Tony asked me to do this, and I'm happy to because you're a good guy and a friend. So today's speaker is our friend and colleague, Henrique Reggiani. Most people here probably know Henrique as that Brazilian guy who does high-resolution spectroscopy and measures precise stellar parameters and chemical abundances. He is that. But what's most impressive to me and humbling is that he overcame significant obstacles by strength of will and work ethic. The least of which was in school, he had to avoid gun violence and ignore pessimistic advice from elders. His family could not afford to pay for an academic track education for him, so he went to IT vocational school and started a full-time work at age 17. Ultimately, he worked as a software developer for IBM and also as a food truck cashier, just in order to pay for night classes in physics, and that enabled him to obtain his physics Bachelor of Science degree. He was accepted into the University of Sao Paulo for a master's degree with Silvio Rossi, and that was on carbon enrichment in halo tracers, which included chemical abundance analysis of Arillari stars, which is quite difficult. For his PhD, Henrique worked with Jorge Melendez on differential abundances in metal pore stars, and that was later awarded with the best 2019 astronomy PhD thesis for the University of Sao Paulo. That work enabled very precise differential chemical abundance measurements in metal pore stars and included evidence for planet engulfment by one of the stars. He spent 1 year at MPIA working with Corinne Lind on non-LTE effects on potassium-1, and the resulting paper is simply the best non-LTE potassium-1 work. As a graduate student, he also found time to volunteer helping underprivileged kids that had suffered various forms of abuse. He then, after his PhD, moved to Johns Hopkins University with Kevin Schlaufman working on galactic archaeology, and finally here as a Carnegie Fellow in 2021. For two recent papers with Kevin Schlaufman, one on extreme velocity stars in the halo and the other on iron-rich metal pore stars, both of those groups of stars are likely accreted from dwarf galaxies. Henrique found iron peak abundance patterns that indicated nucleosynthesis by sub-Chandrasekhar mass type 1a events. Then he also did abundance analysis of bulge star, metal pore bulge stars, and for that he found quite the opposite. He found nucleosynthesis by Chandrasekhar mass type 1a supernovae. So there were two kinds of galaxies and two kinds of type 1a supernova. He's continued his exoplanet work, including a paper on the hot Jupiter WASP 77AB, and which showed that the planet formed beyond the water ice line. And he's had another paper recently on Beta Pic b. Henrique, it's an honor for me to introduce you and to know you. To you and others leaving this year, I really appreciate all of you, and I will miss your support and friendship. Today, well, I thought Henrique's talk was one title, but it's something else. So I thought it was exploring stellar galactic archaeology, but it might be something different. But take it away, Henrique.
Thank you very much, Andy. I don't know what to say from this introduction. It was extremely lovely. Thank you so much for this. The title of my talk is Exploring Galactic Archaeology, but I divided the talk in two separate smaller talks. Like Andy said, I did a lot of different work here. I worked on this iron-rich metal pore stars. I worked on planet adjacent studies. I worked on various different things. And I thought that the best way to end my time here is to give a colloquium on the thing that I actually said I was going to do in my project when I applied for this postdoc. So something that is hopefully coming up shortly, and something else that I just submitted, and Andy is also a co-author, which is the Beta Pic paper that he mentioned, and I'm going to talk a little bit about that. So it's going to be galactic archaeology and exoplanets, generally speaking. and 2 subtitles. The first one, precise astroseismic ages for metal-poor red giants and their impact on galactic archaeology. So I'll go ahead and I'll start, and I hope you guys are gonna enjoy. So when you're talking about because stellar ages are so difficult for us to actually determine, we usually, in chemical evolution of the galaxy formation, what we do is this. We plot something, chemical abundance, as a function of metallicity, and we assume that as the metallicity goes up, the ages of the stars are younger. So the younger stars should be here, the older stars should be there. Though that is not necessarily true, and it is a time when a lot of people are thinking about how can we turn this x-axis into actual age, actual time, instead of some sort of abundance or something that tells us something about time but is not necessarily an actual age. So a lot of works have been trying to do this, and I'll show a couple of examples. So this is a work from Spitoni to 2019. They were measuring ages by means of astroseismology. That means they use the scaling relations to get astroseismological measurements. And what they have is this. So you can all forget about all of the contour plots. These are models. What matters to us at this point are the actual points. So you see a lot of points in green, a lot of points in purple. These are just different places in the galaxy. So one is thin disk, the other is thick disk. You see that there is a lot of dispersion on the alpha to iron, but generally what we expect is that the stars of the thick disk have higher alpha abundances, and we can see this here. And you can see that they find ages like for the thin disk, you have younger ages. For the thick disk, you have somewhat higher stellar ages. But one thing that I want to show with this plot, do I actually have the pointer here? Yes. Okay, much better. So what I actually want to show at this plot is that regardless of the star that you're analyzing, the metallicity of everything that they're measuring doesn't go lower than about -1. And that's because when you're doing astroseismic ages with the scaling relations are based on the sun. So when you change the structure of the star, you have less metals, the star evolves differently, and the scaling relations just fail for anything below about -0.5 to -1. Well, you can do other kinds of measurements too. You can try to do isochrone fitting to a bunch of stars, get their carbon, nitrogen, and oxygen abundances, and you have a correlation between chemical abundances and age that you calibrated, and then you can measure ages based on their chemical abundances. This works, it is good, but it also depends on where in the galaxy you're looking at. The relation between an abundance and an age will be different for different regions of the galaxy, and it will be different for different galaxies because chemical evolution doesn't evolve exactly in the same way wherever you're looking. So this is another example. And also when you're doing this, you need a lot of resolution, a lot of chemical abundance data for you to actually do the calibrations. And you kind of run into the same problems where you can only do this to metallicities of about -1. Okay, so I'm mostly, when it comes to metal per star, to galactic archaeology, I'm interested in metal per star. So what happens when you actually go to the metal per end? And by that, I mean below about -1.5. Well, you have a couple of options. First option is a work that I am collaborating with from David Nataf, which is let's get the ages of subgiants. Subgiants are great. They are leaving the subgiant branch just for a little bit of their time, just left the main sequence, not quite giants yet. So ages of subgiants should be accurate to 10% at least. But if you actually plot isochrones of a same year for subgiants of 13.7, 10, 8, and 6 with different metallicities, there are overlaps. So there are actual problems in constraining even ages of subgiant stars if you don't know the metallicity precisely. And my Cassie student this year actually worked a little bit on that. And okay, we're back. So she got 2 stars from this sample, which is the David Nataf sample. And as you can see, you can't see anything below -1.5. There are points here, I promise, but just we don't know what's happening there because there's a lot of dispersion. And as Isa showed, the ages that they inferred using their photometric method of inferring subgiant ages can be quite different if you do some different type of analysis. And as you can see here, they don't agree with their uncertainties. Okay. So subgiants might not work that well for metal poor either.
I guess I didn't understand. You have 2 different columns, sets of
So-
columns. What are the 2?
Okay, so here is the work from David Nataf. He used photometry to get isochron ages for the subgiants. Here is the work that my Cassie student did this year, in which she got actual metallicities from high-resolution spectra and used the metallicity she inferred to put priors for the isochron analysis. Therefore, she got quite different ages for the 2 stars that she sampled. We actually got 3 stars, and all 3 were different, but the last one we found out it was because of high rotation, so we didn't include here. Okay, so subgiants don't work that well either. So what about giant stars? Well, if you want to do giant stars, you want to do astroseismology. Why? Because astroseismology provides you some constraints on the internal structure of the stars through the oscillations that we can see that are coming from inside of the stars. So they should be able to provide us enough information about the internal structure that you can actually constrain their age to a position better than about 20–30%. Okay, and people have been trying to do this. This is a work from 2014 by Epstein. And what they were trying to show is how well does that work for giant stars with astroseismology. Now, the important thing here in this plot is the difference between the position of the stars in the mass range and this gray shaded regions here. Why? Because the gray shaded region is what we expect the masses of long-lived stars in the halo to be. So they have to be about 0.8 solar masses to 0.9 at the most. Otherwise, they would have already evolved and we wouldn't be able to see them if they're actually old. But when you use the scaling relations to get the actual masses and therefore ages of these giant stars, you get masses like 1.1, 1.2, 1.3. They don't match at all. Well, doesn't matter. People continue to try and do this. And here you can see the same stars that were studied in Epstein by 2 other different works, or 3 other different works. And you can see things are getting a little bit better. They're almost at 0.8, but not quite there yet. And these are still using scaling relations. But what people have been doing is that they're getting the scaling relations and they are updating the scaling relations to account for the metallicity effects. So for metal poor stars. So what I am doing is a little bit different. I'm still using isochron fitting, but I am including more data. So if you include more data, in theory, you have more constraints. So how do I do this? Okay, so first I get stars from a catalog by Sharma, 2021, for metal poor stars that have both delta E and Emax. Those are the astro-seismic observationals that we get. And I make sure that for all of the stars, I have at least something tells me that it's metal poor. It should be below -1.5. And then I do micro observations with them. I have a lot of data on those stars. I do your regular spectroscopic analysis. I get temperature, surface gravity, metallicity, and then I do an isochron analysis. And for isochron analysis, I include photometry. And for all of the stars, I have at least 1 near UV point. I have optical points, and I have at least 1 near IR point. So these are the different sources of data that I'm getting my photometry from. I have priors on extinction for all of the stars. I have Gaia parallax, my spectroscopic inferred metallicity, and my distance priors. I'm using the Bailey-Jones catalog for that, and the astroseismic data. So when I include all of those things in my priors, I do the isochrone analysis, and I check if the metallicity from the isochrones and the metallicity from my spectroscopic analysis agree. If they don't, I do it again, and I keep doing this until they agree. It usually takes about 2 to 3 iterations for the metallicities to actually agree with each other. And then I assume the temperature and surface gravity from my isochrone are my true parameters, because I'm getting temperatures from a lot of photometry. I'm getting surface gravity from parallax, so they should be more reliable. And my metallicity from the actual measurements of my spectra. And of course, I also have ages, masses, radii, etc. from the isochrone feeding. So what I did is I have this sample that I've been observing, and I wanted to test if this works. So I got my mic data, observed it for a lot of stars, and I included one star from a globular cluster, more specifically M4. So M4 has a metallicity of -1.18 and an age of 11.5 plus or minus 0.4. And doing this analysis for one star in M4 that actually has astroseismic measurements, I got an age of 11.43 plus or minus 1.5 and a metallicity of -1.15 plus or minus 0.15. So I can actually reproduce the age and the metallicity of the globular cluster doing this. Of course, metallicity is not that unexpected. Go ahead.
To be clear, the log G or the mass, those come from the theoretical models or some very specific star models?
Yeah, some specific star models. So I'm using missed isochrones. I'll go a little bit into that when I talk about the uncertainties that I have here. But I'm only using the missed isochrones for the analysis so far.
So are there any binaries in these samples that you can never compare with the masses?
That's one of the goals. And I have binaries in my full sample, but they're not included here. This is like preliminary work. We wanted to see if it actually works. Okay, so I did this for 9 stars, including the M4. And I'm going to show the result for 8 of those because I'm excluding M4 from this plot. And these are the masses that I get for these stars. I actually do retrieve masses that are expected for stars of this age in the halo. Okay, so I'm confident now that I'm doing at least a reasonable job actually getting masses and ages for these metal poor stars. So let's look at the actual masses and ages of these metal poor stars. I know everyone hates to look at tables, but I really wanted to show this one. I wanted to show it for 2 reasons. First, I want you to look at the uncertainties here. And I will be honest right away. These uncertainties are too low. These do not include any systematic uncertainties. I'm only using missed isochrones, and I'm doing a Bayesian analysis. So these are just representative of the posterior distribution of possible wages inferred my feeding method, and doesn't actually include any systematics. Now, how can I include systematics? That's another step. We actually have to get different isochrones and do the same exact process, same exact code with different isochrones. The code that we have for them at the moment just works with missed isochrones. We have an undergrad student working on that. Now, the other interesting thing is because all of them have Gaia data, I can try to see, well, where are the stars coming from? What are the substructures in which the stars from my sample are? Because I'm not choosing for substructures. I'm just getting stars from K2 that have astroseismology and metallicities, etc., on the range that I want. And you can see here, I find stars from basically everywhere, from Gaia Enceladus to the Milky Way thick disk, from the Milky Way halo, in situ halo, retrograde halo. I have stars from everywhere. And the one interesting thing that I found on this test is that I found one star from Gaia Enceladus with a quite young age, 9.5 gigayears, while the other 2 stars from Gaia Enceladus are pretty much the same age, 13.4. So if we didn't find anything more interesting, we did find that the Gaia Enceladus has an age range of at least 4 gigayears. So star formation in Gaia Enceladus was still ongoing after at least 4.5 years. And now we see those stars today. Okay, but like Andy said in his introduction, I like doing chemical abundances. So I also, because I have this nice spectra, I can look at the chemical abundances of all of these stars. And unfortunately, what I see is that they're basically normal halo stars. There's a little bit of a scatter here, there's a little bit of a dispersion, but if you look at the background points here, the background is just halo stars from different works, and the stars in my sample, they fit right in. So chemically speaking, they just look like halo stars, except perhaps there's one more metal-rich star, which is a little bit higher than usual. And I'll talk about that in the paper, but we're not completely sure yet, but it might have been something to do with type 1a supernovae. Well, and if you look at the other abundances, I'm just showing abundances of alpha elements, iron peak, and now I'm showing some abundances of the odd Z elements. They're pretty normal. And I also say neutron capture elements, nothing special about any of these stars, which is kind of good because if I want to see if my method works, I want to test it on stars that behave nicely. And these stars appear to behave nicely. But I promised ages, so what about the ages? Well, not great. I don't see anything. Do you guys see anything? It's just a bunch of very old stars with one Gaia Enceladus young star here. I don't see any correlation here. By eye, it appears to be something like this, which would be strange. But when we actually try to do statistical analysis, cross-correlating the ages with several different age indicators like lithium, magnesium, calcium, we actually didn't find any statistically significant correlation between the ages and any sort of chemical abundances, even though we only use this very tiny age uncertainties that I mentioned before. So this is what I promised to do. I promised to do this for a lot of stars. I have now about a spectra of about 92 stars, if I remember correctly, to do this. So we are hoping to get a paper out showing the method that we are using and then actually work on this large data set that I've gathered since I got here at Carnegie. And I thought it was a good way of showing at least partially how I spent my time here. So do we have actual conclusions? Yes. So we can get 10% precision in relative ages. We don't get 10% precision in accuracy. We don't have 10% precision in accuracy. But for relative ages, if you want to study how the galaxy evolved through time, yes, we can do that if we have the astroseismic measurements of these giant stars. Surprisingly, one of the most sensitive parts of getting the actual age in our analysis was extinction. Actually having a good prior in extinction can change the age up to 4 gigayears. So this was when I was testing it out. If I add some too high or too low extinction, ages change completely in the isochrone fitting. So the importance of extinction, I think it often goes overlooked when we're talking about stellar analysis, and I wanted to point that out. So this is a path of high precision studies, chemical dynamical evolution of the older stars population in the Milky Way. We didn't find any age chemistry correlation so far. And interestingly, Gaia Enceladus, we found populations from 300 million years after the Big Bang and also 4 billion years after that. And like I said, our next step is to perform a high-scale analysis. Well, I forgot to update it with my last observations, about 90 stars. Yep, go ahead.
The fourth conclusion, I know it's a small sample, but it seems counterintuitive.
It is counterintuitive, but I think it's also because if you look at our actual sample, we did find stars from very different places in the galaxy. So it's difficult for them to be correlated with abundances if they were all formed in different environments with even slightly different chemical evolution that would change how the correlations work. So that I think that's why we don't see any correlation in there. Okay, any other questions? Go ahead, Tony. Sorry.
So for the GSC, have you looked at the positions of the stars within the distribution, like on the sky of the GSC? Is that interesting to think about?
I haven't thought about it, to be honest. I don't know how interesting that would be, because I don't know if there are differences in the GSC based on the position in the sky. I will have to look into that.
Yeah, I mean, just generally speaking, yeah, it's surprising to me. I mean, I would have expected there was one star forming event. There's probably a pretty small,
Yeah.
stellar mass, probably would have blown out much of the gas. They have 4 billion years of, I mean,
The
that's
difference. It could have been like when the GSC started falling into the galaxy, probably more star formation happened. That way, it could have been 2 separate events of star formation because of the infall of the galaxy into the Milky Way.
Yeah, if that's the case, so you might want to sample multiple submersion positions to see if there's a correlation.
Yeah, yeah. But we are getting the where the stars were formed afterwards, because the goal here is to actually not, initially at least, was to actually not choose my sample based on that. It's just getting ages and seeing how that correlates. And then we look at Gaia to see where they're from. James?
Just wanted to add to that point, we see the same thing in H3. That I think Anna wrote a paper that says the infall was something like 10 gig years ago, but the age distribution of H3 goes up like 8.
Okay. Oh yeah, and the how we say where our stars come from is actually from the selection of the H3 selection. Karim, you had a question?
Yeah, I mean, there are more than 10 metal core subgiants observed by surveys already, right?
Yeah.
So much of this analysis you could do just taking the parameters from apogee or something. Is the parameters that you get from surveys the limiting step in the age precision?
Yeah. Yeah. We do have some somewhat different parameters from that differ from apogee. And the problem with apogee, which is the same problem as Galar, which is the same problem as Lamos, is that the metallicity precision is quite limited at the metal poor range. Their atmospheric models only go the lowest metallicity of their models is -3.5. So when you start get close to 2, to -2, the actual metallicities that they infer can be quite different than the metallicities we infer.
Right.
Tony?
So I have 2 questions from mine.
Yeah.
Corrections for your iron over hydrogen.
Yes. I included the corrections from Anisha Maisi 2016.
And then with iron 1 citation equilibrium help your extinction?
If it helped my extinction issues, I'm not entirely sure. I don't think I tested those things in conjunction. What I can say is that for these stars, I do have equilibrium between ionization balance, but I don't know how much of a difference it made to help with the extinction. I have to look that up. Okay, then as I promised, how I can use this type of study that I do on different things. I'm going to talk about this, how stellar characterization shapes our knowledge of exoplanets. So I'm sorry for the brusque change in subject, but I wanted to highlight different things that I have been doing in my time here. But I'll continue to talk about stars. And I just wanted to point out that work has been submitted 2 weeks ago, and with a lot of people, including John and Andy from here, from Carnegie. So I'll continue to talk about stars, but I'll be very specific that when I talk about stars from now on, I'm just talking about FGK stars, this range of temperatures, this range of surface gravities. Why? Because this is the range for which beautiful spectra like that allows us to get some very specific abundance measurements that we need to interpret exoplanet formation, migration, and other things. So what I'm just saying here is this. Basically, we can get all of these things very precisely if you are in the range of basically FGK stars. It's reliable. Okay. So what's the actual role of this type of spectroscopy when you're studying exoplanets? I'll be very exoplanet people will forgive me for this. But for me, there are just two types of exoplanets. There are giant exoplanets and small terrestrial exoplanets. Just that. When I talk about giants, I just care about the hot Jupiters because those are the planets you can actually see the atmospheres. So giant planets equals hot Jupiters. And well, people have been getting abundances for hot Jupiters. They look at the hot Jupiter's atmospheres, they get carbon, they get oxygen, they get all sorts of stuff. So how does the abundances that they get for the exoplanets help us interpret how planets form? All of this kind of things is what I'm interested in. And more specifically is, what's the role of this host star in all of this story? That goes overlooked a lot, apparently, in the literature of exoplanets, unfortunately. But there's also the other type of exoplanets, small, tiny ones like Earth. For those, when you're trying to study internal structure constraints of these exoplanets, we're basically getting masses and radii of these exoplanets to get their density, internal structure, etc. But masses and radii of exoplanets are tightly correlated with the measurements of masses and radii of the host stars. So that's what I'm interested in. Also, there are other things like if you can have abundances of certain chemical elements in these planets, which we can't, the only place we can get these abundances currently is the stars, we can actually have an idea of how their internal structure is. Like, for example, if you want to have tectonic plates, you need to have some sort of radioactive material providing energy to create the magma below it and etc. On Earth, we know it's thorium and potassium. So we need to measure these types of things. Okay, but what I'm going to talk about is the first one, giant planets. This is a giant planet, this is the star. What I'm going to talk about is formation of exoplanets. So back 2011, Oberg put out this idea that you can correlate where a giant planet was formed and how it migrated based on its position, based on the abundances of certain elements. So basically carbon to oxygen ratio. Why carbon to oxygen ratio? So this is, this plot here shows the sun, basically. So solar-like star. It's right here. So when you go away from the star and in the protoplanetary disk, you start making some molecules turn into solids, basically. It goes from the gas phase, it changes gas phase into grain phase, basically. And these are the ice lines. So at this position is where H2O becomes ice. At this position, about 10 AU is our CO2 becomes ice, and CO here. So these ice lines. So depending on where the planet forms, because you have different ratios of gas to grain, it's going to have a different ratio of carbon and oxygen because more carbon will be trapped in molecules or more oxygen will be trapped in molecules. So if you know the carbon to oxygen ratio of the planet, theoretically, you can have an idea of where it formed and therefore how it formed and therefore how it migrated. Okay, so a few of the conclusions from the paper. Substellar or stellar carbon to oxygen and superstellar carbon, it means the planet accreted a lot of icy planetesimals after the envelope was already formed. So these are the only, I'm just going to go through 3 of them. So hang on with me. Superstellar carbon to oxygen ratio and superstellar carbon. It forms here, close to the CO2 line or CO line, and accretion of sea-rich grains once it migrated to this region here. Okay. Third idea, if you have superstellar C2O and substellar CNO, it formed right here. So basically, this is a simple model. It doesn't include a lot of protoplanetary disk dynamics. So there are a lot of things that should be taken into account, but it does allow you to make some predictions. So I'm going to go with that. As Andy mentioned, I worked on this on WASP 77AB, and I just wanted to highlight an example in which what exoplanet studies have been constantly doing is that they get the abundances of the planet. So these are the abundances of WASP 77AB, which is just a hot Jupiter around a star that is much like our sun. And they say, okay, so that star is much like our sun, and therefore let's just compare it to the sun. So they compare it to the sun, they compare it to Jupiter, Saturn, Uranus, and they compare it to solar composition based on asteroids, and they take their conclusions out of that. But when you actually look at chemical abundance distribution in actual protoplanetary disks, these are all really close to us, within 100 parsecs, because basically we can't see a lot of this distribution if you go far. And you see it's only molecules that you can see. And for these different systems, it is very clear here, the abundances don't actually matter. What matters is that the curves are quite different. So even in the thin disk, solar neighborhood, at about 100 parsecs from us, the abundances of different species are very different in different protoplanetary disks. So just comparing them to the sun is incorrect. And I'll show you another plot that shows that. So this is the distribution of carbon to oxygen ratios as a function of metallicity for the solar neighborhood that comes from Galan, the survey Galan. And this is where the mean density is. And this is the sun. So even the sun doesn't have a carbon to oxygen ratio that matches the mean carbon to oxygen ratio of the solar neighborhood. So assuming the sun, you're actually wrong, because it's more likely for your star to be here. Okay. I think I've tried to say enough about why I'm doing this, and I'm going to talk about, like Andy said, Beta Pic B. What is Beta Pic B? Beta Pic B is a hot Jupiter around Beta Pic. Beta Pic is an A star, temperature of about 8,000, and most importantly, a VSNI of about 113 kilometers per second, which means this is what the spectrum of Beta Pic looks like. This is a Mike spectrum, resolution of 30,000 of HD 181327. 30,000. This is Beta Pic harps, 115,000. Signal to noise 1,200 according to the authors. And as you can see anything. Like I said, we want to do carbon and oxygen. Where is carbon? Carbon is this little thing here. Where is carbon? I have no idea. So it doesn't work for Beta Pic. Not because, just because the star is not helpful. What do we do? It's just super young and massive. It's still slowing down. It's so Beta Pic group has a dynamical age inferred at about 30 million years old. So it just left the main sequence. It's still rotating quite rapidly. Well, but as I just spoiled, Beta Pic's quite young, and we can still see its moving group. So Beta Pic is moving along with a bunch of other stars, and this is Roy 2020, where they selected stars from the Beta Pic moving group, and these yellow cool things here are the stars that are moving along with Beta Pic. So this is the Beta Pic moving group. So our idea is, well, if we can't study Beta Pic, why don't you study something that was formed from the same molecular cloud? It should have the same chemical abundances. So the abundances of star, one of the stars, should be a better representative of the protoplanetary disk around Beta Pic, even than Beta Pic itself. Also, because I didn't mention this, but A stars, they have chemical peculiarities. I'll show them to you shortly. Well, we looked it up. These are all of the stars in the Beta Pic moving group. There are only 2 F stars. Everything else is M stars. We don't want to do M stars. M stars are very, very complicated. These are very cool. So we observed these two stars. So we observed all of the F stars, FGK stars in Beta Pic moving group. What did we find? Well, for one of the stars, it was rotating too quickly. We couldn't do anything. So we could get metallicities, we could get good metallicities, good everything, but it couldn't actually get carbon and oxygen, so we just pretend it doesn't exist. But for HD 18, 13, 27, we actually can do quite a good analysis. This is its spectrum. As you can see, the lines are very well behaved. You can see everything that is in there. So we actually did the whole analysis on HD 18, 13, 27. Just call it HD for now on. And we got rotational periods from tests. We got dynamical ages. We got isochrone ages. Everything works pretty well. So we got an age of 60 plus or minus 30. Dynamical age of the group is 30 plus or minus 20. So we got the same age. We got reasonable temperatures. And most importantly, we got carbon and oxygen abundances. That's what we wanted. We corrected our carbon and oxygen both for non-LT and 3D effects. And you can see the 3D non-LT carbon to oxygen ratio right here. Now that's 0.62. The sun is 0.59. So in this case, if people had interpreted based on the sun, it would actually have been better. Now, as I said, we wanted to use, yeah.
If you convolve the HD star to proper Doppler bombing, does it actually make a good match to Beta Pic?
I haven't tried that.
Because I'd be curious to know if there were still some systematic residuals where the carbon oxygen features or where the carbon features are, right?
I don't know.
I'm going to assume it's the same, certainly like the features.
So there's also another problem. So Beta Pic is an A star. A stars are known to have some chemical peculiarities, some differences in its chemistry that we don't exactly know where it comes from. It's some sort of chemical stellar evolutionary effect, but you don't know exactly what it is, so you can't correct for it. And I'll show that in a second. So what I was going to show next is, so I said all these things, oh, let's get stars from the same moving group. So does that work? Well, it should. This is 2018. This is a bunch of clusters, all stars that were formed together. And the dispersion in abundance, it's tops 0.1. And it depends on how good the spectra is. For a good spectra, the typical difference star-to-star variation that they found is like 0.02 dex, which is basically the uncertainty in the analysis, not actual dispersion. What happens when I compare this HD star with Beta Pic? So these are abundances that were either detected or some upper or lower limits for Beta Pic based on that HARP spectra. I work from Safi et al. 2021, which I should have put here. And these are the abundance, the difference between the abundances of Beta Pic and HD 18, 13, 27. So a 0.6 to 0.8 difference in aluminum, magnesium, it just doesn't match. So the abundances of Beta Pic are not a good representative of that molecular cloud because of the problems with Beta Pic. Okay, so in the paper, we're also proposing, so if you want to study exoplanets, what do you do when it comes to how do you compare your carbon to oxygen abundance? Well, if you can, to the whole star. If you can't, some other star formed in the same molecular cloud, so a moving group, open cluster, globular cluster, etc. And then you can do mean abundances in the galactic substructure observed, so basically solar neighborhood, which means C2 of about 0.5. If all of the above fails, then you can use solar. Otherwise, don't use solar. We also did a reanalysis of Beta Pic B itself. So this is a JWST spectrum of the planet, of the hot Jupiter Beta Pic B. And we did our own retrieval of this data. There was an existing retrieval by the gravity collaboration. This is what they inferred. And I want you to focus on the metallicity that they inferred for the planet, 0.5. We found a metallicity, so scaled to the same abundances we are using to the star, 0.08. Now I'm going to go back, sorry, and I'm going to show you the metallicity that we found for the actual star. 0.05, this is LT, when you include the non-OT correction, 0.1. So we actually think we're doing better because now our planet and our star appear to have the same metallicity. Okay, so what does that mean for actual planet formation? So this is the plot I showed you before, and this is just a diagram showing, well, if I divide this in 4, each one of these places has a different interpretation for how the planet was formed. And let's put our star in here. This means for Beta Pic, it accreted a lot of oxygen, mostly oxygen-rich planetesimals after the planet was formed outside of the CO line, which is not included here, but it's outside of the CO line. So Beta Pic should have been formed around here and accreted a bunch of planetesimals. So it's so much planetesimals, it doesn't make any sense. That being said, GMT workshop last week, someone found another planet around another star at the Beta Pic moving group. They found the star, that planet to be in the same region as Beta Pic B, which is weird. Anyway, here I am showing so this is the Beta Pic being interpreted by the solar abundance and the Beta Pic being interpreted by the solar abundance with the gravity collaboration retrieval, and in blue our retrieval, and we change it to stellar. So here is stellar with our retrieval, stellar with the gravity team retrieval. It changes a little bit, but the conclusions are pretty much the same. So in the case of Beta Pic B, we didn't change any of the conclusions from previous paper, but we did emphasize the importance of exoplanets and elemental abundances and how you should interpret the formation of planets. Oh, I should have taken this off. This is, and basically Beta Pic B formed beyond the H2 ice line and accreted large amounts of icy planetesimals. And with that, I'd like to thank you all, and also thank you all for the time here. It has been great at Carnegie. I'm sad that I am leaving. And I hope to stay in contact with you all. Thank you.
Excellent. Here, wait for the microphone, please.
Hey, thank you very much. It was very interesting. This could be a very basic question, but I know nothing about the subject. Can you please go back to the diagram you showed with the 4 different regions? So do you expect in other systems when you adopt solar abundances versus the stellar abundances that the difference will be so large that it will change the interpretation of where the planet was formed?
Yes. I should have a plot about this here. Plot about this here. Yes. So this is the previous star planet that I worked with. This is WASP 77 AB. So if you assume solar abundance, it formed in this region. If you assume stellar abundance, it formed, so it actually changed the region in which it formed. So previously they concluded it formed inside the H2 ice line. They didn't only use this as an argument in the paper. They had a little bit more of an interpretation. But when you do the stellar analysis, it changes quite a bit. And the large error bars here are mostly because we included uncertainties in the planetary analysis that they didn't previously included. So in some cases, it does actually change the interpretation. I had some other, there were some other examples of people doing this in this GMT meeting, in which you had changes that went from here to here, from here to here. So it does represent, it can be a significant change. Now, one of the things is that most of the planets that we can observe, we are focusing them on certain types of stars, and that kind of bias things a little bit. It's mostly because that's what we can observe when it comes to planet atmospheres. And there is a lot of planets around M stars, and dealing with M stars can be difficult, can be tough. So oftentimes they just do the solar analysis. And someone, if you like M stars, start doing that. You'll get a lot of papers out. Yeah.
Other questions? So one question I had is, have you talked with the people that think about migration, and are they troubled by this amount of migration, or is this, are they happy? And this is easily explained by the sort of migration scenarios people usually invoke for Jupiters.
The migration scenarios are okay, as far as I know. I think when it comes to, like, for WASP-77, it formed, according to this, close enough to the position where it is as a hot Jupiter now, that it's not a problem to deal with. The actual problem, okay, let me. So no one really expects planets to be formed here, to be in this part of these diagrams, because not only you have to migrate a lot. If you do a back of the envelope simple calculation with this abundance here, it would have, after the planet formed, after the envelope accreted, so you have a gas giant that's pretty much formed, it's going to be as it is for the rest of its life. As it is migrating inward, for this planet to be here, it needs to accrete about 300 Earths worth of oxygen. It's a lot of oxygen, like a lot. So how does it actually do that? Is it a problem with the retrieval? I don't think it's a problem with the stellar side, because if you assume solar and if you assume stellar, it's pretty much the same because it's really close to solar for this particular star. Now, another retrieval of another planet in the same moving group have been positioned in the same part of the diagram reinforces that either you have some systematics in the retrieval of planetary data that we don't know of, or, well, that's theory, people. We have a lot to do on how planets form, which I guess was expected on the WSG launch.
Is that more of a problem with having enough mass in the disk, or just the time scales that you'd have to be accreting over? Yeah, okay.
Both. I am not entirely sure what would happen if it was not migrating at the time. But because it is migrating and there is this change in how much oxygen is trapped in planetesimals, it has to accrete all this like 300 Earth masses of oxygen quite rapidly before it gets to a position where you don't have any oxygen in that form.
All right. Any last questions? No, thank Henrique again. Thank you.